All right, good morning, everyone. Welcome back. Before I get started, does anyone have any questions from the last time that they want me to go over, or anything we should look at before we get started? Nope. Okay, I will get going then. All right, so the first thing I want to do today is to actually talk through another one of the operations. I was hoping to do both of these last week, but we clearly got bogged down on the one operation, the inline mapping operation that we looked at. So today I want to work through a second one, which was the copy operation, to actually, look at how another kind of operation goes through the pipeline. After we're done with that, I will proceed on to looking at some of the internal runtime services that we have: processor managers, message managers, memory managers. And if we don't get through all those today, which I don't think we will just continue them the next time. Okay, so let's start off with the operation class. So just to refresh everyone, we're going to go back into legionops.h. And last week we were looking at the map op. So we were looking at class map op. So this is the inline mapping operation that we were looking at before. Today I want to look at a different operation, which is the copy op. The copy ops are just another kind of operation here. You see we're extending the public copy class, which is our interface for the mapper to map copy operations. These inline copy operations, if you haven't used them before, are for doing copies directly between two different logical regions, most likely from different region trees. And the obvious reason that you want to do this is that we initially didn't have this operation and people were writing their own tasks to do copy routines. But we have a bunch of copy infrastructure inside of the Legion runtime, and we said we tend to do copies much faster than anyone's going to write a task to do it, and so we can actually do much better if they actually tell us that they want to do a copy from one region to another. So that's the general idea of this copy op. You'll notice here that this copy op is a little bit different than the inline mapping operation that we looked at last week, and it's a little different because we're extending a different base class. In this case, we're extending the speculative op abstract class. We looked at speculative op very, very briefly last week, but I want to actually look at it in some more detail today, so we're going to get into that. But speculative op does extend the base abstract operation class, so just like the inline mapping operation that we looked at last week, this copy op is still one of our generic operation classes. You see the copy operation class is pretty simple. It extends a bunch of the virtual methods that we have on our operation class that we looked at before. We implement some of the virtual methods from this copy base class that we need for our mapper to access in order to say what kind of operation this is. And then we have a couple of data structures for doing our analysis. But really, it's a pretty simple class for doing an operation. Okay, so let's actually walk through the copy operation, walk through how it goes to the pipeline, just to go over this again. I really want to get this sort of process of how these operations go through the pipeline into everyone's head. And so we'll start at the beginning, where the copy operation call comes in from the high-level runtime. So I'm going to jump back here. We're going to go back to runtime.cc, which is where we have all our entry points. Actually, we can do it the right way. We'll start in legion.cc, which is where it really comes in. And then we'll go and see where that pops out into runtime.cc. So if I search, let's see. If I search for the copy launcher, this is the declaration of the constructor, but here we go. Here's our call that comes in from high-level runtime, issue copy operation. We turn around and call issue copy operation on our internal runtime. So we jump back to runtime.cc. And if we search for issue copy operation, here's our entry point back in from the high-level runtime call. And okay, so the first thing we do is we get a new copy operation object for us to use for this copy op that's been requested by our application. This call to get available copy is going to go and get a copy operation from one of those pools that we talked about last week that the high-level runtime maintains of all the different kinds of operations. So when we come back from that call, we'll have a copy operation to work with. We have two different versions, again, of this initialization routine. If we're in debug mode, we do a bunch of checking for things like dummy contexts and is this a leaf task, so we're not allowed to be doing launching and stuff like that. And then eventually we call this copy op initialize call. And you notice the same thing happens in the non-debug path as well. The main difference is in the debug path, we actually let you check all the privileges, which can be a little bit of a dynamic overhead. So we like to avoid that. In the non-debug case, we set that to false automatically. But other than that, everything is pretty much the same. There's some extra logging messages in the debug path, but nothing that's going to change the actual correctness of the execution. So if we go look at this initialize call, let's actually just see what that does. So if we go back here to legionops.cc, we're going to go look at the copy operation initialization call for copy out, initialize. Oh, if I can spell. There we go. So you see, this initialize class is going to do effectively what it's doing is copying over all the fields from this launcher class, which is what the applications create when they say they want to do a copy out. So down here, we're copying over our source and destination region requirements. Note that we're using the copy without mapping info call that we talked about last week, which allows us to copy just the fields from the region requirements that we actually care about. We then initialize the mapping fields, which are the fields that weren't copied, so that everything is nice and initialized. Notice we add the special no access flag onto our region requirements. So we know that the copy ops are never going to need to create region accessors like tasks do. So this gives us a little more freedom in the mapping to actually be able to map to memories which are not visible from any particular processor associated with where this copy operation is being mapped. And that's what this no access flag is doing here. You'll see that there's actually an application level flag. We just set it here on the copies just to make sure we don't want to have people have to forget that this exists. Effectively, we want people to map copy operations wherever they're going to run. And then this loop here is copying over the source region requirements. So these are the region requirements that are describing the source regions for our copy. And then this loop right here is copying over the destination region requirements, which are where we're going, which are the destinations for each of our copies. And you'll notice that in the documentation for these copy ops, we have to have one-to-one source to destination requirements, and that each of these region requirements can have at most one field, so that we know how to line up fields with each of the different requirements. We have some checks here for simultaneous coherence, which we're not going to get into. We record some of the synchronization operations that users might have asked. So if they ask for us to acquire grants, or if we have any phase barriers that we're supposed to be working with, we know how to copy those into our actual operation. We copy our mapper ID, our tag. If we've been asked to check privileges, this is where we go and ask. We check each of our region requirements to make sure that they meet the privilege constraints relative to our parent tasks, or our parent task. And so we have a whole bunch of calls that go and actually check that we actually meeting the privileges and requirements of the copy operation. But this big if statement is really everything inside this if check privileges is all just error checking code that we can turn on when we want to. And you see where there's a bunch of error checking code. There's lots of messages here that can show what can happen when you go wrong. Okay, I'm going to ignore the privilege and mapping paths today. We'll get into that when we talk more about mapping. And eventually down here, we come out of, we do some logging here for some of our logging infrastructure. So everything wrapped in these ifdef legion loggings or ifdef legion prof or legion spy, we can skip all these. And eventually we're done with our initialization. Okay, so let's jump back to runtime. We'll go back to initialize our issue copy out. Okay, we've done our initialization. So we're now past this initialization phase. If we're going to do in-order execution, we want to remember our termination events. We can wait on it. We eventually, we do our checks again to see if we have any, if our parent task has mapped any regions which are going to interfere with us. If we do, we go through and actually do the unmapping of them, and we unmap them. We then issue our operation to our dependence queue. Actually, let me say a little bit more about this, because I don't think we saw this with the inline mapping code last week. One thing that we have to do when we launch sub-operations, and this wasn't true of the inline mapping class last week, but if we're launching sub-operations like subtasks or one of these copy ops, one of the things we want to do is actually check to make sure that the parent task hasn't mapped a region, a logical region, which we're requesting privileges on. And the reason for that is that if we end up waiting on our parent task, the parent task can't finish finish. And so we end up getting this nice circular deadlock. So the runtime actually does a check to see if the parent task is going to have any mapped regions which are going to interfere with this. And if it does, what we do is we then unmap those regions, we launch our operation into the queue, and then we launch new inline mapping operations to remap those regions. This allows us to get the right effect and avoid any deadlocks, but at the cost of possibly more mapping operations going through the queue. So what you see is, I'm not going to go into this call today, but there's a call here to find conflicting regions, and we pass in a vector of unmapped regions. And we pass in our copy app, which has all the information about our region requirements, which we're going to be requesting privileges. In this context is that single task object that represents our parent task. So it has all the information about which regions have been inline mapped inside of that parent task. And what's going to return back is a list of physical regions which we need to unmap in order to actually be able to run this copy operation without deadlocking. So if it returns any unmapped any regions that we need to unmap, we go through and we issue the unmap call. And I'm not going to show this today, but this is going to launch an unmap operation into the pipeline that'll flow through the pipeline before us. Notice it's before we put ourselves in the dependence queue. So it's going to be ahead of us in the dependence queue. It'll make sure that the unmapping gets done first. We then put ourselves in the dependence queue, add ourselves to the pipeline. And then after we've added ourselves, then what we can do is we want to make sure we maintain the illusion that the same regions that were mapped when we came into this launch copy operation call are again mapped when they come back out. So what we do is we then remap these physical regions that we unmapped up here in this loop. So again, if we had anything unmapped, we go through and we create a new map op, we initialize it, we put everything in, and then we add it to the dependence queue. Importantly, we need to actually wait for these mapping operations to finish before we can return all, because the enclosing parent task actually expects that those physical regions are still mapped. So we have to actually wait for these. So what we do is we keep track of all of their completion events, the events for when they've actually completed their execution stage of the pipeline. We can merge all these together. This call right here is a low-level runtime call that merges a couple of events together and gives us back a new event. We can check to see if it's triggered. If it has triggered, or if it hasn't triggered, we're going to actually need to wait on it. We have some calls that we always need to wrap around waits for the high-level runtime, which we'll get into a little bit later when we talk about processor managers. But right here, when we call this, yeah, go ahead.
I had a quick question about the cost of remapping.
Yep.
Is it does the cost grow as a function of the size of the region that you're remapping, or is the cost relatively constant?
The cost is pretty much constant relative to the size of the region. It's
okay.
Pretty much a function. It's mainly a function of the number of regions that you have to unmap and remap.
I see. Okay.
Yeah, this is the great thing about regions is they can be as big and small as you want them to be, and the overhead associated with them doesn't change.
Excellent. Okay.
One important point there. Yeah, sure. One important point there is that we sort of have this illusion to make sure that applications are run correctly every time. But we encourage users to actually try to keep unmapped regions unmapped so that when they launch subtasks and copy operations and so forth, they don't have this cost of having to unmap and remap implicit in the runtime. And one of the cool things that we're hoping that Elliot's compiler is going to be able to do is actually be able to avoid a lot of this, because it knows about this trick of keeping things unmapped or explicitly unmapping it itself and then only remapping it when it really needs it. And so really this is, we're providing correctness guarantees inside the runtime, but at the cost of extra dynamic analysis and possibly extra inline unmapping and remapping operations.
Hey, Mike.
Okay. Yeah.
So it seems like what stage of the pipeline are we in again for this?
We haven't even launched anything into the pipeline yet.
Oh, this is before
This is before. Well, sort of. This is our entry to the pipeline. This add to dependence queue that I'm highlighting.
Okay.
Here.
So the thing that seems interesting to me here is the wait call implies that this stack frame is going to be active while we're going through the pipeline.
That's right. You definitely expose latency. You definitely expose latency if you have to unmap and remap.
Well, and more importantly, there's like interesting sort of concurrent event sort of stuff going on because of that.
Absolutely. Absolutely.
Okay.
And yeah, that's the thing to realize is that when we put these operations into the pipeline, that is entirely an asynchronous operation, right? We're kicking them into the pipeline, and the Legion runtime is going to go through and walk them through the pipeline. Meanwhile, this parent task, usually will return if we don't have to do any of these unmap and remap stuff. This is an asynchronous call that's going to put the thing into the pipeline, and then we're going to return, right? And we're going to be able to keep running. And right, you're entirely correct that there's lots of concurrent things going on as the runtime is processing these operations in parallel with the parent task's execution. Okay, so just to wrap this part up, if we did have to remap any operations, we keep track of all the low-level events that correspond to when they're actually completing, and we put all these in one of these set of events. And we do this low-level runtime call to merge these events together to give us an event that will trigger when all of these events have triggered. And if we have to wait on this event, if it hasn't triggered yet, we can actually block waiting on this event. Now, this will actually block the parent task from executing any farther. And really what we're going to have to do is keep this processor busy. Then we're going to have other tasks that we run on it. This wait call, though, will actually block the processor, and the low runtime will actually go through and schedule something else onto this processor if there's other tasks waiting to run on this processor. So that will happen automatically. We won't, even though we're blocking the task, we won't necessarily block the processor that we're running on. These pre-wait and post-wait calls, like I mentioned before, we're going to get into these a little later when we look at the scheduler that's inside of the processor managers. But really, just anytime you're going to call wait on a user level, on an application level task, you just have to call pre-wait and post-wait. And then, if we had already triggered, this is the end of that if block up here from this if unmapped regions empty. Or I guess it's, let's see. Oh, here's the end of the if regions unmapped empty, and then this is the end of the if block if we even had any unmapped regions. If we're doing in-order execution, again, we can wait on the termination event for the operation that we just launched. So this term event comes from up here. Notice that we pulled out the completion operation for this copy out to know when it's actually finished running through the completion stage of the pipeline. We can block on that if we're doing in-order execution, and then we can return. And that allows the parent task then to continue running. Okay, so there's a little different view of how these operations get launched and some of the things the runtime does to do things correct, to maintain correctness for our applications. Okay, I'm not going to follow this added depends queue because we saw it last week. We know it goes into the processor manager, and then it ends up eventually calling triggered dependence analysis inside of the copy app, so we can actually jump back to the copy app and look at where that call is going to come out. So I'm jumping back to Legion Ops for a copy app, trigger dependence analysis. Here we go. This call is, again, very simple. We start off with our begin to dependence analysis call. Here's a slightly different aspect of this copy out. One of the things that you may or may not have noticed on Legion copy apps, but they're one of our operations which can be predicated. You can actually specify a predicate which says whether or not this copy operation is going to be run. This predicate can come from a future from some other task. But effectively, what's going to say is, if this future evaluates to true, then we should run this copy operation. If it evaluates to false, then we should not run it. So what this register to predicate call, this is actually a call on the abstract base class of copy app, which is a speculative op, which we're going to go look at. Actually, let's do that now. Let's actually go look at where register predicate is declared, and then we'll see where it's defined. So if we go back to legionops.h, we search for this predicate class, predicate op. I do some, or sorry, speculative op. That's what it was. Here we go. Speculative op. Notice that we provide a implementation of this register predicate dependence. The idea here is that we actually want to register a dependence. So the predicate is going to come from a predicate op, which is actually flowing through the pipeline. It had to be issued. So we launched some task which gave us back a future. We then launched another operation which gave us a predicate based on that future. And now what we want to do is register a dependence on that predicate operation, which was launched into the pipeline before us, and then we're going to have our copy class or our copy app register a dependence on that predicate operation that's flowing through the pipeline as well. And the reason for all this is that we're building up this big dependence graph of operations and how they depend on each other based on the region requirements as well as their futures and so forth. We want to make these kind of dependencies explicit. Let's actually go look at this register predicate dependence real briefly. I'm going to jump back to legionops.cc. I'm going to search for speculative op, register predicate dependence. And what you'll see is that really all this does is look for the predicate, which we saved when we initialized our copy op. This is predicate is a member field of a speculative op class, and we registered it when we initialized our copy operation. Actually, let me just show you. We called copy op initialize. Notice we called initialize speculation here, which initializes all the base fields. And one of the things that we passed in here was this launcher predicate, which is a reference to a predicate operation. And if we look at speculative op initialize, cannot spell initialize today. You'll see that this predicate value that came through right here. There's a couple different values for it. If it was true, in which case we know the true predicate is effectively just a built-in value for this predicate. And if we know, in that case, we know that we're going to automatically resolve to we know that we're always going to run this operation. So we can mark that our speculation state has already been resolved to the true state. If it's false, then we know that we can already resolve to the false state, and we don't need to actually track the predicate operation at all, because there is no predicate operation. These are effectively constant types, or constant values for predicates are always true and false. You can always have those. But then if we actually do have a real predicate, we actually have a reference to an operation. We'll probably look at that a little bit later, where these predicate operations come from. They're just another kind of the operation class that goes to the pipeline. But if we actually have a real one that's not null, then we have to mark that, we haven't resolved our speculation yet. So effectively, we haven't figured out what the value of this predicate is. So we have to go look at that at a later time. And that's effectively when we mark the speculation state to pending map state, it really just means wait until we actually try to map, and then you can check if we've actually resolved the value of this predicate to know whether or not we're really going to run the operation or not. Importantly, what we do is we add a reference so that this predicate operation is never going to be garbage collected back from runtime. And we'll talk about garbage collection a lot later. Okay, so let me jump back to the speculative op. Well, actually, it's right here, register predicate dependence. So you see when we come in here, this call to register predicate dependence is really just saying, add a reference, if we do have a predicate that's not null, add a dependence to it saying that we're going to depend on its value as part of our execution. Okay, let's go back to copy op, trigger dependence analysis. Okay, so we're registering a dependence on our predicate, which we obviously have to do in order to know whether or not we're going to execute or not. And then what we do is we go through and perform dependence analysis on each of our region requirements. So you remember last week we saw the inline mapping operation invoke this perform dependence analysis, which is on the region tree forest. And the copy app is doing the exact same call. The only difference is it's doing it for a whole bunch of region requirements. So we're iterating over all of our source requirements in this first loop, and then all of our destination requirements in the second loop. But it's using the exact same call that the inline copy operation that we looked at last week. And we'll go look at that in a lot more detail later. Not today, but significantly later. But really, this is just going to the region tree and performing the dependence analysis to figure out which other operations we depend on. And then we're done. We call end dependence analysis, which removes all the guard references that we added in the based operation class as part of doing this dependence analysis. And it may end up triggering our execution. Okay. So one of the things, normally after you've done your dependence analysis, the next time an operation gets woken up is when it's ready to map. This may not be true for operations which are possibly speculative. And so one of the things that can happen is that we can actually have our predicate operation that we depend on actually tell us that it has resolved its value. And if that happens, the speculative class has a couple of methods for handling that. So let me jump back here. Let's go look at speculative op again, just to show you what's going on. So if we search for a class speculative op, here we go. So we'll notice that there are a couple of calls here that all of our base classes have to implement for speculative op. These are pure virtual methods. So one is we have to check to see if we want to speculate at any point in time. Another thing that we have to check for is whether or not is what happens if we resolve our predicate value to be true, in which case we're going to continue executing our operation. So what happens when that occurs? And finally, we can also have one for what happens when we resolve to false. If our predicate ends up being false and we don't actually want to run the operation, what do we have to do that? And what you're going to see is that some of this gets gets triggered by some of the modified implementations of these trigger calls that are intercepted by the speculative op class. The most important one of these is actually trigger mapping. So let's actually go look at what happens to a speculative op when we call trigger mapping. You recall that the inline mapping operation, whenever trigger mapping was called, would jump immediately into mapping the operation. We would go through and immediately start trying to map it. We'll see that that's not the case for these possibly speculative ops. So if we look at trigger mapping here. Okay. So trigger mapping, in some cases, we actually know what the right answer is. So if our predicate is null, there's a couple of things that we might already, so remember the trigger mapping, it's called once all our mapping dependencies are resolved. So this is effectively the next wake up that could possibly come in for our copy operation. But instead of it being handled by our copy operation, it's being handled by the speculative op class. It provides its own implementation of trigger mapping that's special for any general type of operation which can possibly have a predicate that it depends on. So if we're null, we already know the answer. If our speculation state is marked to resolve true, then we can call our resolve true method, which will tell our operation to effectively keep running. If our speculation state was false, then we know how to resolve false. And when we're done with doing this, this will end up cleaning up our operation and telling it that we're done. We don't need to actually run because our predicate resolved to false. And when we're done with all this, we can immediately return because we're done with this operation. Whatever is going to happen, happened. Now, there's a third case, which is that we actually had a real predicate, and we haven't necessarily resolved its dependencies yet. We don't actually know what its value resolves to. So the first thing we want to do is register ourselves as a waiter on this predicate, saying we would actually like to know when this predicate has a value. So remember, predicates come from futures. So futures don't necessarily have a value immediately, so it's possible that this predicate doesn't even know what its value is yet. So what we're going to do is try to register ourselves as a waiter on this predicate operation to be notified as soon as it knows what its value is. And one of the things we pass in is we actually pass in a value that can be set by the predicate if it already knows its answer. And we get back a Boolean saying whether or not this value is valid or not. And once we've actually registered ourselves as a waiter, we can remove our reference that we added when we did our initialization. And the reason for that is that now, effectively, we don't need to keep track of the predicate. It's going to tell us when it knows what its answer is if we've successfully registered ourselves. Okay, the first case here is that, let's say, for example, that the predicate doesn't actually know what its value is yet. The future that it depends on hasn't actually triggered yet, and so it has no idea what its value is. So it will return successfully registered, but this valid will be false, meaning that this value wasn't written to at all. So we don't know whether it's true or false. Well, one of the things that we can choose to do here, and this is one of the things that we're still in the process of implementing all the infrastructure for, is we can actually ask our mapper if we would like to speculate on the value of this predicate. Sometimes mappers will know that predicates tend to return true or tend to return false. So for example, if I had like an iterative conjugate gradient solver, I might create a predicate that represents my loop having, or my convergence criteria that says whether or not my iterative solver has converged or not. and I'll predicate all the next operations in the loop based on that predicate value. And most likely, this predicate is always going to end up being true, saying that we haven't converged yet. And so we know that most times it's going to be safe to speculate that we haven't converged yet. And so in that case, the mapper might have special information about that kind of a predicate to be able to say that it's better to speculate that the value is going to end up being true, and we can actually start running the operation even though we don't know what the predicate is going to be yet. It's also possible that this mapper can also return false here, saying that it doesn't want to speculate. It's perfectly valid for the mapper to say, I don't know what the answer is going to be, so I don't want you to speculate at all. In which case, we're going to block at this point of the execution of this part of this operation until it actually knows what the answer is for the speculation. Okay, so there's a whole bunch of different values or different, well, I've overloaded the term value here. There's a whole bunch of different values that we can have for this value field as well as this valid field. And they're going to determine what we're going to do next inside of this operation. So depending on what decisions were made by the map, by what the value of the predicate was and what decisions were made by the mapper, we can end up in a bunch of different states. So there's this switch statement here inside of the operation lock here is really figuring out exactly which state we should be in for all the different kinds of speculation predication that can occur here. Just to walk you through some of the basic ones, well, actually, we can see two of the easy ones here. Resolve true state, we already know the answer, we can break. Resolve false state, we can break. The interesting one was if we're in the pending map state, if we got back a valid value, if the value is true, then we can go to the resolve true state and we can continue true execution. If it was false, we go to the resolve false state and we mark that we want to continue false. The other possibilities were that we actually were speculated. In this case, if we didn't know that the value is valid, else if we speculated, then we can guess that the value is true, and we can mark we go into the speculative true state and continue execution. Otherwise, we mark that we've speculated false. This will actually cause us to not begin executing the operation, but we're not going to clean it up yet because we know that it's still a possibility that it might actually end up resolving true. And then if the mapper decided not to speculate on the value, we're just going to stay in this pending map state, which marks that we're not going to do anything until we actually get a notification from the predicate saying exactly what the value was. And then we don't want to trigger any of these while holding the lock, so we have to wait for us to release this lock here, pop back out of the operation lock. And once we do, we can call the right operations based on the state of our speculative operation. So coming back to our copy operation is effectively a special kind of speculative op. The speculative op classes here is handling all of the correct logic for how to deal with speculation so that we don't have to know about that stuff inside of our copy op. And so if we notice, if I search for copy op trigger mapping, we're not going to find it, right? There's no trigger mapping call because the speculative op is handling that for us. Instead, what the speculative op handles, instead what the copy op actually has methods for are these trigger or continue true and continue false, or what do we call them? What did I call them? Let's see if I can find it here. Sorry about this, having a brain fart. Here we go, resolve true and resolve false. So notice that these resolve true and resolve false calls were pure virtual methods in the speculative op class, but they were invoked by the speculative op class once it knew what the correct answer was for the predicate. So the resolve true case, in this case, we know that we've resolved our predicate true, and the speculative op class has told us that we know the right answer. In this case, this actually mirrors what the original inline mapping operation does on trigger mapping, which is add ourselves to the local queue, which says we're ready to actually start executing this operation. At this point, this will put the copy operation on the list of things to map, and it will go about continuing its execution. If we resolve false, what we do is we immediately mark that we're done executing mapping, and what this will cause our operation to do is to actually progress through the pipeline as if we were already done, as if there was nothing to do, which is actually what the right effect is for our predicate resolving false. So if we resolved our predicate false, we're just going to plow right through our pipeline and allow natural process of the pipeline to clean up our copy operation and pass everything through. We just have to trigger the right stages of the pipeline to make sure that it continues through the pipeline and gets done. This is the third call. This is, by the way, that speculate call that the speculative op class can invoke if it notices that the predicate hasn't actually resolved a value. And what you see is that for the copy op, this is doing a very simple thing. What it's doing is it's getting our executing processor, the processor where we were launched from our parent task. And then we're going to go ahead and ask the runtime to invoke the mapper to check whether or not we want to actually speculate on this value. And again, what we're going to do is we're going to return a Boolean saying whether or not the mapper wanted to speculate or not. And we're passing in a reference to that the mapper wants to guess is the right answer for the speculation. And we won't look at this today, but this is just going to go through and make it's just plumbing to get through to the right mapper for the right processor that our runtime is maintaining. But it's going to go ahead and anytime you see this invoke mapper, you know that call is going to end up calling one of our mapper objects to actually perform an operation. Okay, so this is mainly, this speculative aspect of this copy op is mainly one of the differences from the inline mapping operation that we looked at. But again, just like the operation class, which abstracts a lot of the machinery for doing operations, walking operations to the pipeline, the speculative op adds the necessary machinery for abstracting how to deal with operations which can be speculated or predicated. And what you'll notice is that a little later we'll look at tasks in more detail, and tasks will also extend that speculative op class because they can also be predicated. So again, we've wrapped up all the machinery for how to deal with speculation or predication and speculation inside of that speculative op class. Once we've been added this local ready queue, we know we're actually going to have our trigger execution invoked. So right down here, we have our copy operation trigger execution method, which is going to be responsible for actually doing the mapping for all of our different copy operations. So I'm not going to go into too much detail here. There's a lot of similarity between how the inline mapping works and how this copy operation trigger execution works. Effectively, what we do, just to give you the high-level view of it, for each of our source requirements, we have to do our pre-mapping. So you can see the call here for the region tree forest to pre-map the physical region. Remember, we did pre-mapping for our single region requirement in our inline mapping operation last week. This is the same loop for the destination region requirements. Again, we're doing our pre-mapping on our our region tree forest. If we didn't succeed in pre-mapping, we can exit out. We can return false. At this point, we know we're ready to map, so we can ask the mapper to go through and map this copy operation. So we can pass ourselves. This is going to go through and ask the mapper to pick memories for each of the region requirements that this copy operation is requesting and do all the normal things that we expect from the mapper. Once we get back the results of the mapper's request, we can actually try to map these physical regions. So again, for all the source requirements, we try to, again, we invoke the region tree forest to ask it to map the physical regions based on the region requirement requests from the mapper. Down here, we do the exact same thing, except for the destination region requirements that we have. So again, we're asking the region tree forest to do the mapping. If we've actually succeeded in mapping, we were able to map all of our region requirements. And at this point, we can actually issue the copy operations across from the source region requirements to the destination region requirements. I'm not going to go into a whole lot of detail about how this works. After it involves doing some more operations on the region tree forest for registering the physical regions for our source and destinations. There's a special region tree forest called method called copy across, which we'll look at later, that talks about how to copy from one physical instance to another in an efficient way. But I'm not going to dig into those details today. Eventually, what ends up happening is we end up coming down here, and we end up there's a bunch of logging calls in here that I'm skipping over. I'm skipping over a bunch of the phase barrier and reservation operations we do. But eventually, we get down here where we've actually completed our mapping of this operation, so we can call complete mapping. If the mapper asks to be invoked and told about the answers, we can call notify result. And eventually down here, we can do our operations for actually triggering the execution of this operation. Now, one of the details here about this copy op of how this triggering actually occurs for calling for completing this operation is a little different than how the inline mapping operations worked. So one of the things you'll notice is that, I'm not sure if I mentioned this before, every operation has completion events, which is a low-level event which marks when this operation has finished the completion stage of the pipeline. And one of the things we can do is this is actually a user event, which is a low-level runtime primitive, which hopefully Sean will begin talking about a little later this week. And a user event is just a low-level runtime event that we can trigger ourselves. We can effectively call trigger on it. And normally what we can do is we can actually call trigger directly and just have it trigger immediately. But in this case, we don't want to do that because we actually know the condition. We know it's going to trigger in the future. We know it's not safe to trigger it now. We haven't actually finished the completion stage. But we know we can trigger it once all the events, the low-level events that came back from our copy operations are ready to trigger. So this copy complete event, let's see, we can actually find the merge event for it up here. Here it is. So we issued all of our low-level copy operations from our source requirements to our destination requirements. We got back a set of low-level events that we put into this copy complete events. You can actually see them being inserted right here, coming back from these copy across calls that I told you about. And what we're doing is we're merging these together into a single event that says when all of those copy operations are actually done, we can actually use that copy complete event down here to trigger our completion event for this operation. And then we can mark that the operation class no longer needs to trigger it because we've effectively issued the trigger in advance of actually completing this operation. Now, there are two things that we might end up needing to do here. You'll notice that you may recall from last week I mentioned that we don't necessarily need to call complete execution right away inside of our trigger execution call. So we want to mark that we only want to trigger our execution completed when we've actually done all those copy operations actually being executed. So if our copy complete event hasn't triggered, if all of our copies aren't done yet, what we want to do is actually defer that call to complete execution until we know that all of the copy events have actually been finished. So this here is an optimization for triggering the completion event as soon as possible. We want to defer the call to the complete until we know that it's actually done with all the copy operations. The way that we're going to do that is to use this high-level runtime utility task that we looked at, I think, 2 sessions ago, which is effectively we can launch our high-level runtime meta task, and we give it a special ID saying this is the call that we want to invoke once we've actually triggered this copy complete event. This deferred complete operation is another variant of this high-level runtime meta task, and this is sort of its subtype, the deferred complete ID saying, what to do. We can fill this in with some arguments about the operation that we're doing this deferred complete on. And so what we're doing is we're recording ourselves, and then we're launching a task on one of our utility processors saying, don't actually call the completion until we've actually done all the copies for this operation, or done all the copies that we actually requested as part of this copy operation. The alternative here, and what we're going to see is that this call is going to come around and call this virtual method, which operations have, called deferred complete. In the case where this copy complete event is already triggered, we can actually call it right away. But if not, we end up launching this high-level runtime meta task. And just to remind you where this pops back out, if we go look at runtime.cc, let's see if I can remember where this actually, I believe this is all the way down at the bottom of, let me actually drag this all the way down here. I believe it is all the way at the end. Yeah, here we go. This is our high-level runtime meta task. Remember, I think we looked at some of the other calls that actually came in here before, like deferred mapping and so forth. And here's the special case for the one that we just launched, which is a deferred complete operation. You'll notice that as we can get our list of arguments that came through, we know that there's an argument on there called proxy this, which is just a reference to the operation that wanted us to call deferred complete. And it turns around and calls deferred complete. So that's where the deferred complete comes through. The only difference between where we saw it here being used in Legion Ops was that we deferred this task launch on a low-level event, corresponding to when all the copy operations were actually done. Going back to copy up. copy up, trigger execution. It's a slightly long method call. Right here when we launch this task util spawn, the last argument here is this copy complete event, which means we don't actually run this call until this this copy complete event has actually finished. And if we look at what happens when we actually call deferred complete, the method is right here. Once we're done, doing deferred complete, we can mark that we've actually completed our execution, and we're actually done doing all the copies for our copy operation. So effectively, this is just an example of one of these cases which I talked about earlier, but I don't think I showed you an example of just because we are in an operation or in a stage in a pipeline for an operation doesn't mean that we have to do all of the calls to mark that stage completes before the function returns. Effectively, you can do these complete execution calls at any time from pretty much anywhere. And so you can defer them as long as you want, and the operation class will know how to handle them correctly coming back in whatever order they come back in. Okay, so that's how we actually launch our copy operation. We've converted into a bunch of low-level runtime copies via the calls to the region tree forest, which we didn't talk in a lot of detail about. But once we're done, we can defer our complete operation until we know that all those copies are finished. Okay, I think let's just jump back here and look at look at the copy op class just to see if there are any other methods that were interesting. Class copy up. Right, so we looked at trigger dependence analysis. We looked at trigger execution. We looked at deferred complete. We looked at resolve true and resolve false, as well as speculate. And we saw that these came from this this abstract speculative op class in order to give us a concrete instance of this copy op. And report alias region requirements is just a special function for handling cases where we notice that region requirements for an operation have actually been aliased with each other. And so we're not going to get into that today. Let me just, I claimed a little earlier, just to show you that the speculative op class actually is used in a couple other places. Just to show you that actually it gets used by task operations, which are another kind of, well, let's actually see, there's a couple of places, I think, in here where speculative ops come up. The copy is a kind of speculative op. We can see that acquire operations are a kind of speculative op. For those of you that probably haven't looked at some of the tutorials in a lot of detail, the acquire op is a special kind of operation for dealing with simultaneous coherence to actually allow us to mark when it is safe to make copies of regions which have been mapped with simultaneous coherence. But it's another kind of speculative op, so again, you can issue them speculatively. And then the companion operation to acquires are releases, and this is another kind of speculative op. We're back to the copy, but also there's another kind of speculative op, which if we look in Legion task.h, we search for speculative op here. Here we go. We can see right here that the base kind of tasks, this task op class, also inherits from speculative op. And this will be important because all of our tasks are going to be able to be speculatively issued with predicates as well, marking whether or not they should actually execute. Okay, I've only got about 10 minutes left, so I don't want to dive into some of the resource managers today with only 10 minutes to go. So what I'm going to do is actually take a look at some of the predicate operations in a little more detail, just because we've got about 10 minutes, and that's about a good amount of time to look at what actually goes on inside of some of these predicate operations that go through the pipeline. So for those of you that have actually used predicates, which I imagine are not too many people, what you'll notice is that if we look at a launcher here, so if we look at, I'm looking at the task launcher class here, which is how we launch single tasks. You notice that we can pass these predicates in as arguments, and we keep a predicate for this task that marks whether or not the class has been, or whether or not this task has been predicated. If we actually look at this predicate class, here are two, it's a very simple class. Here are two baseline, effectively our static special kinds of predicates, which are true and false. If we know we always want to predicate true or we always want to predicate false, then we have very obvious, well-defined values for this predicate operation. The alternative is that this can actually reference a predicate impl class, which is effectively an operation that represents a predicate value. So the operation class is going to proceed through the pipeline just like any other operation, but its job is going to be to figure out the value of this predicate. And what you'll notice is that there's a couple of different ways to create predicates inside of the Legion runtime. So if I search here for create predicate, you'll see that there's a couple of methods here. So the first way you start creating predicates is usually what you do is you pass in a future. And this future has to be a Boolean future in order to be able to get to be able to work correctly with predicates. So notice we say this future must be a Boolean future. So if your task returns a Boolean future, you can create a predicate. There's a very easy way to make a Boolean future out of any future, which is if you want to test a condition on a future, you just pass the future in as an argument to another task. The job is to evaluate the condition of the future relative to some value, and then have that return a Boolean. So you can just use the natural deferred execution model of launching tasks to test things to create Boolean futures if you have a non-Boolean future. And what we give you back is a predicate that represents a Boolean that we can then pass as arguments to other other operations like tasks or copies or so forth. Notice we also support basic logic on predicates. So you can negate a predicate, you'll get back a new predicate. You can AND two predicates together to get back another one, or you can OR two predicates together to get back another predicate. Let's actually see where these pop out inside of Runtime CC, just to show you what goes on and that these things actually go through the pipeline as well. So if we jump back to runtime.cc here, we know that this is where all of our operations are going to pop out. So if we search for create predicate, put colons on this. Here we go. So here we come in. We come in with our future value, saying we want to create a predicate from this Boolean future and give us back a predicate value. There's some testing here for different error conditions. We want to make sure that our future is good and stuff. We want to make sure we're not in any bad cases for our parent task. The most important thing we do is down here. What we do is we get an available future predicate op. So a future pred op is another kind of operation inside of our operation class, or that extends our operation base class. We can get a predicate op. We can make a predicate based on this predicate op. We initialize this predicate op with the information about the future that's going to actually need to reference in order to return its value. There's some stuff here for in-order execution, but eventually we stick this future predicate op into the operation queue just like anything else. And then it's going to go, and then we can return the predicate value. It just references this future predicate op that we created. So again, predicates don't necessarily need to evaluate their values right away. They're just going to defer their execution and figure themselves out later once they know the value of the future that they're associated with. Just to show you what goes on inside this future pred op, so we look at legionops.h. If we search for class future pred op, again we see that this class again is extending another intermediate class, which is the predicate impl class. So if I actually can't remember the predicate impl is in this file or not. Yeah, here we go, predicate impl. This is the base kind for all kinds of predicates. So we'll have future predicate ops, we'll have and predicate ops, not predicate ops, and or predicate ops. They all extend this base predicate impl class. And you'll see this extends the operation class, just like everything else. The only difference, so this is the base class for predicates, and you'll notice they have special methods for just doing some basic operations on predicates, like adding references and removing references to make sure things are not garbage collected too early, which I'm not going to talk about. But if we look at, let's jump back to future predicate op. So we're extending this predicate impl. And you'll see that we only really need to override a couple of different methods here in order to actually implement our operation class for future predicate op. So we're overriding trigger dependence analysis. We're also overriding trigger mapping. So let's just look at what goes on, and then notice that we're storing our future that we're going to reference as part of determining what our predicate value is going to be. So if we jump back to Legion Ops, we search for future pred op. Here's our future predicate operation class. It's actually very simple. You'll notice that pretty much there's only a couple of things that we have to override. So if we override trigger dependence analysis, so again, we do the begin and end dependence analysis trick. Notice there are no region requirements on this future pred op. So what we do is we call register dependence. And what we do is we're actually registering a dependence on the task that our future value came from. We look at our future value, we look at its implementation, which is our actual internal object that represents that future. And then we're going to register a dependence on its task and its generation. So this is important. This is another way that we can have data dependencies between operations, which is normally we get them based on region requirements and regions the tasks are using. But we can also get them through futures that get passed through predicates or futures that get passed directly as arguments and so forth. So we can have data dependencies either on regions, which you can think of as large sets of values, or we can have them via futures, which are much smaller individual values, which tasks depend on. But they all go through the same process for registering dependencies. And so what we do is we have our future pred op register dependence on the task that's generating the future that it depends on. And then what you'll notice is that the only other method that we overrode here in the operation class, we could leave all the rest of them the same, was this trigger mapping call. And so the idea is what we're going to do is once we're ready to trigger our mapping, what we're going to do is we're going to try and get a Boolean value back from our future. If it tells us we passed in a valid value and we also get back a possible value for the Boolean, this valid bool is saying whether or not the value is actually valid or not. So if it's not valid, or if it is valid, then we know the value of our predicate and we can resolve ourselves. If not, what we do is we have to add a reference. We add a reference to ourselves, and then we launch a little helper task, again using this high-level runtime meta task, to defer the resolution of this predicate value until the future has actually resolved itself. And once the future has resolved itself, then we can go get our value and set our value based on the results of the future. At this point, we can call complete mapping, and then trigger execution will call trigger execution and so forth, and it'll be very easy to go through the rest of the pipeline, and we don't actually need to override any of those other methods. Okay, and then these predicate ops serve as the basis, the implementation. Notice that we jump back here just very briefly. I know we're almost out of time. We search for future pred op. Notice that this implemented the base predicate impl class, and this predicate impl class was the pointer kind that we stored inside of those predicate objects. A pointer to a predicate impl was what was stored inside those predicate handles that get passed around. So whenever we pass around predicates, effectively all we're doing is referencing these kinds of operations which go through the pipeline to resolve predicate values just like anything else. So when I tell you that everything goes through this operation pipeline, I literally mean everything. And there will be a reason for that. And the reason is that we'll see is that lots of these operations, we're building up a big data flow dependence graph based on operations and their dependencies using regions and futures and so forth. And having them all use the same infrastructure for remembering this information is going to be useful when we talk about how to deal with both scheduling as well as looking at resiliency and handling misspeculation of tasks and operations and so forth. But quite literally, everything goes to the operation pipeline, including even the resolution of predicates and very simple things like that, all go through the operation pipeline. Okay, so I'm out of time for today. We didn't get as far as I wanted to. We just effectively finished up our second round of operations. I promise the next time we will start something new. We will start looking at the processor managers and memory managers and message managers and all the different services that the runtime provides for actually doing execution. Specifically, when we look at processor managers, we'll get to see a little bit of how the scheduler starts to work for the Legion runtime. So hopefully that will keep everyone interested in the next time. I think on Wednesday, Sean is going to start talking about the low runtime. We should finally have him get going. And so everyone that's been waiting for the low runtime or to hear about the low runtime, hopefully we'll grant your wish on Wednesday. Okay, does anyone have any questions before we stop? No? Okay, I think we're done for today. I'll see you guys all next time.